Hello. Right. So, okay. Well, it's 4 p.m. So let's get started. So, hi, nice to meet you. My name is Jason. Today I'm going to be talking about public key authentication on embedded systems. Right. So it's a bit of a mouthful. I promise you, by the end of this, you'll have an idea of what it means, why it's important, and a general idea on how to implement them on something like an Arduino. So, just as a brief self-introduction, again, I'm Jason. I am a third-year student at the University of Waterloo. I specialize in security. I've done some work with the cryptography field as well as the security engineering field. So yeah, let's quickly take a look at what we're going to be talking about today. So as a quick agenda, it's fairly straightforward. We're going to start off with a 15-minute talk about what authentication is, why it's important, as well as sort of some applications of authentication for embedded systems. Then we're going to dive into cryptography. This is going to be very light on the math. You're not going to need to know any math about it. I'm going to talk about it from a very high level. Then we're going to do a demo where I'll actually implement this public key authentication system on the Arduino. And last but not least, we will have 10 minutes for any Q&A as well as closing remarks. Just as a quick note, if you guys do have questions throughout the presentation, just put them in the chat. I'll be taking a look at them periodically. So there's no need to wait until the end. You can just put them in and I'll answer them whenever I have the time. So, right, so let's talk about authentication. So why do we authenticate? Well, the first question, I suppose, is what is authentication? Authentication is a term that commonly is used interchangeably with authorization. And semantically speaking, this is actually incorrect. Authentication of proving the identity of the requester. Authorization, on the other hand, is the process of ensuring that the requester actually has the sufficient permissions or rights to carry out whatever action that they're looking to do. So let's think of this as an example. So I go into a fictional bank, I walk up to the teller, and I ask them, hey, I'd like to withdraw $100 from my account. So the first thing that they're going to need to do is that they need to ensure that I am who I claim to be. So they're going to ask for some form of ID. Either I give them a driver's license or I do something like I show them, I put in my PIN number. So at that point, I have proven myself to be who I claim to be, myself, Jason, or the account holder. And at which point they'll carry out to make sure I'm actually authorized to withdraw money from the account. So odds are what they're going to do is that they're going to look up my name in a list of people that's allowed to withdraw money from that specific account. So that is essentially authentication, is me showing my ID. Authorization is ensuring that I can actually withdraw money. Now, key thing is, without authentication, this authorization step is completely useless because I can just go in and claim, I'm Bill Gates. I'm going to withdraw $200 million from the bank account. And they're going to be like, oh, yeah, that's fine. So essentially, authentication ensures the integrity of the authorization step. So that is essentially authentication in a nutshell. So why do we care about authenticating? Obviously, from the point of a bank, it's important because you don't want people just walking in and withdrawing large sums of money without actually having a good record or ensuring that they're actually allowed to withdraw money. Hey, William. So that is, from the perspective of a bank, it's obvious why we care about authentication. But from an embedded system, well, why do we really care to authenticate, for example, an Arduino? There's not much of doesn't seem to be much of a need for it. So I'm going to talk a little bit about a situation that I've actually encountered back in the day when I was working with an Arduino. And it's this. So it's fairly straightforward. What we have is an Arduino. The Arduino is connected to a bunch of sensors. And essentially, whenever an event happens, whenever a set of data points come in, it's going to send it over to the server. Now, because these events happen far in between, there's no persistent connection between the server. Essentially, whenever it needs to update the server, it will open up a connection, a TCP tunnel to the server, send the data, and close the tunnel. The server will then take the data and shove it in a database. So that's fairly straightforward. It doesn't seem to be anything special. Well, the problem is a couple months later, so I had the Arduino stuck in sort of a test rig, and it was doing stuff. And then a couple months later, I was like, oh, well, let's see what's up. So I opened up the server, took a peek in the database, and turned out I had nothing but garbage in there. So first suspicion, well, the Arduino is broken. So, I obviously messed up there. So pop by the Arduino, connected it to my laptop, see what it's sending. And it turns out it's actually sending stuff that's correct. So that's weird. So, well, what's happening? The Arduino is sending correct data, but the server is somehow mangling it or something else is going on. And this is what's going on. we have another computer. We have an unauthorized device that will also connect to the server and send garbage to it. So because the Arduino connects to the server periodically, essentially what the server has is a port that is open persistently. And essentially whenever a connection request happens, it will open up the port, and read in the data, shove it in the database, life is good. Now the thing is, because that port is an unauthenticated port, well, there's no way for me to tell the difference between my actual Arduino and, well, this one, some bot that just sends random garbage to it. So essentially I was just getting garbage in the database. And without authentication, there's no way for me to tell the difference between a correct device and an incorrect device. So, or I suppose an authorized device and a non-authorized device. So while we're on the topic of bots, I'm actually just going to show you guys something to show you guys I'm not just going insane and talking about random conspiracy theories. So this is a cloud server that I have running, and essentially this is the output of an authentication log. So this tracks all of the login attempts via SSH, and you can actually see what's going on. So around a couple of minutes ago, actually, there was an attempt to log in for root, and they tried some random password, which failed. So yeah, so these things are fairly common. They basically try pre-existing usernames and passwords. Some of them try to connect to ports, send in a payload, and essentially if you're running a vulnerable web service, that service gets compromised and they have the ability to do stuff on your server. They essentially get shell access, which is no buenos. So it's essentially out there. Typically, most existing operating systems do a good job of screening them out. For example, I don't actually see this. The only reason why I know people are trying to log in is because I open up the log, but people don't actually get in. So that's what I'm talking about. As a side note, that is also why you don't do stuff like, have your username to be user or root and have your password be password. Don't do it because this thing's going to get you. So that's my rant. Let's get back to the actual important bit. Right, my slides. Right, so essentially that random bot is now sending garbage to my server and polluting all of my data. Luckily, the payload it's sending didn't actually cause my server to do anything weird, so that's nice, but it doesn't fix the fact that I'm getting garbage in here. So what do we need to do? So let's talk about some solutions that already exist. This is stuff, who's they? Why would they do this? They essentially, these are botnets that are typically deployed, and the idea is the botnet needs to self-propagate, meaning it wants to expand. So what it does is it will typically compromise other devices. So, and once that happens, they can use it, for example, to continue launching attacks like denial of service attacks, credential stuffing attacks. These are all sort of methods of sort of like cyber attacks, and they are done via a botnet. But in order to get a botnet, you need to compromise a bunch of devices. And my server would be, if they actually managed to compromise my server, well, that they would have another device on that botnet. So that's why they have these sort of bots running around. So that sort of makes sense. Hopefully it does make sense, and I'm not just babbling random stuff. Let me know if you want me to clarify some more. But yeah, so let's talk about some of the solutions that sort of exist off the shelf. So, and before we do that, let's talk about the requirements. So it's going to be 5 requirements. So the first requirement is the human must be out of the loop. So what does this mean? It means that I should not have to intervene whenever the device wants to be authenticated with the server. So this rules out stuff like, for example, I stick a keypad on it, and whenever it needs to send data, I have to walk over to the Arduino and punch in like a secret code. It's not great. For example, what if the Arduino wants to send something at 2 a.m.? I'm not going to wake up at 2 a.m. to let my Arduino send stuff to the server. So human must be out of the loop. This should be completely automatic without any intervention. Must be compatible with and uses 8-bit processor compatible libraries. So this was way back in the day. This was when really the main sort of chips on an Arduino were AVR 8-bit based AT mega chips. These days, with your Arduino Wi-Fi revision 2s, those are actually using 32-bit ARM chips. So with a 32-bit ARM chip, you have the advantage that you have a lot more library support. You can do a lot more stuff with it. You have more RAM, which makes life great. But because I only have 8-bit chips, 8-bit processors, it has to be compatible with 8-bit processor libraries. Number 3, standardized cryptographic implementations. Right, so this is a huge rule in security. You do not roll your own crypto. Or in other words, you don't try implementing your own cryptographic algorithm. For example, RSA, you do not implement that. You get someone else's implementation because they would have basically been maintaining it. They also typically are implemented by large groups of people. So that's what I mean. It should be an external library. It shouldn't be something you write yourself. And it should be standardized. So what that means is there's a bunch of requirements that large government bodies put together for cryptographic algorithms in order to prove that they are secure. So it should conform to those standards. If you guys are interested in that stuff, check out FIPS 186-4. That talks a lot about digital signatures, and sort of it's a really good example of a cryptographic specification. Bear in mind, it is also 130 pages long. So, bit of light reading. Number 4, it should provide a strong guarantee if it was sent, then it was sent by an authorized device. So this is getting into the authentication and authorized bit. So number 4 essentially states that there has to be some element of authentication to it. If it was sent, we need to ensure that the device is who it claims to be, and there has to be some method for us to check that the device is actually authorized. So that part ensures that someone can't just send stuff to my server anymore. Number 5, it should be reasonably difficult to forge. So this is a bit of a broad description because there are many ways to forge these authentication packets. And what we're looking for is if somebody has managed to intercept communications between my Arduino and the server, is the data they get, can they essentially try to forge an Arduino given that data? So I'll talk a bit about that some more. It sounds a little weird, but essentially, even if they manage to intercept the communications, there is some missing component that ensures that they can't just forge a valid request. Right, so let's talk a bit about some of the existing solutions. So we got 3 of them off the top of my head. TLS with client authentication, passwords, or a VPN. So start with TLS. TLS is a fairly well-known and widely used transport layer security protocol. So what it does is it essentially negotiates a shared encryption scheme between the client and the server. And as a result, you have a secure tunnel between the client and the server. So TLS, it's very difficult to forge a TLS packet because all the data is encrypted. So even if you manage to capture it, you don't get any information out of it. So that's nice. Client authentication essentially means that the client will also authenticate itself to the server by sending essentially a digital certificate to the server. The server will verify that certificate. And if the certificate checks out, then they are able to connect. So TLS with client authentication gets us both the authorization bit as well as difficulty forge. Passwords. Passwords are fairly straightforward. Passwords are under a subset of what we call knowledge-based authentication. So I prove that I am who I claim to be by telling you something that only I know. So that's fairly straightforward. It's fairly simple. I'll talk a bit about why passwords don't really work well in a bit. And last but not least, VPN. VPNs essentially have virtual private networks. You tunnel into a local network, and as a result, you're able to sort of, the check then at that port would be, it will only allow connections from the local subnet. So VPNs are fairly straightforward at the authorization bit, but they have one major flaw. And let's talk about the flaws. TLS with client authentication. So unfortunately, there is no 8-bit implementation of TLS. If you are on a 32-bit processor, there is definitely stuff like embed TLS, bare SSL that allows for TLS on those machines. But with a 8-bit processor, you don't actually have any libraries that support it. You can try implementing your own TLS, but again, that's sort of in the realm of rolling your own crypto. Don't do it. And also, embed TLS can theoretically be compiled for an 8-bit processor, but no one's really tried. Nobody really has any definitive results on whether or not it works or not. So there's that. Passwords are vulnerable to replay attacks. So again, imagine if somebody captures the communications between the Arduino and the server. Well, if they can derive sort of either the password or some transformation of the password, they theoretically can take that password, send it to the server, and get authenticated. There are ways around that. For example, you have password plus the timestamp and stuff like that, but that makes the system brittle. So if something goes wrong, then something will go very, very wrong. So we're going to stay away from passwords, mainly because the solution I'm presenting is better than passwords, in my opinion. Last but not least, VPN. VPNs are just genuinely overkill. They require way more processing power. This is because they exist on top of TLS and they have their own protocol. So it's really way too complex. It's overkill. It's much worse than TLS. The reason why I want to talk a bit about VPNs is because back in the day, I did a similar project with a laptop, and that's how I did authentication. I just made the VPN do it for me because I was lazy and didn't want to implement my own stuff. But when I moved to an embedded device, obviously VPNs were no longer an option. So 3 solutions, none of them work. That is a bit of feels bad. So what do? Well, we're going to implement our own. And to do that, we're going to be using some cryptographic theory in our solution. So before I start really talking about cryptography, I just dumped a bunch of information on you guys. Are there any questions at the moment? I'll take like 5 seconds. Doesn't seem to be any. Cool, life is good. All right, let's talk about cryptography. So bit of a lie, it's not going to be cryptography in 30 seconds, but I promise you at the start, you're not going to need to know much math about it, and you will not need to know much math. That much I can promise. So when we think about cryptography, what we typically think about is encryption. So there are 2 types of encryption. One is symmetric encryption. The other is asymmetric encryption. So let's start with symmetric encryption because it is the easier one to understand. So symmetric encryption essentially has, if we imagine sort of the sender and the receiver, and we draw an imaginary line down the middle, well, the sender and the receiver are both going to look the same in terms of the keys they have. So the sender is going to have the secret key, and the receiver is going to have the exact same secret key. So in order, if I want to send a secret message, what I'm going to do is I'm going to take that secret key, I'm going to run it through the encryption algorithm, and I'm going to get my ciphertext. The receiver will receive that ciphertext, take that same secret key, and decrypt it to get the plaintext, the original plaintext back. So symmetric encryption has quite a few advantages. The main advantage is the fact that it is very, very fast. For example, AES uses substitution and I believe transposition in its sort of encrypting the data. So these are very, very fast, very, very cheap operations. And as a result, you get a really fast encryption scheme. Bad news about this is the fact that symmetric encryption runs into what we call the key distribution problem. Because if you can imagine, if I wanted to communicate with you over the internet, well, we're going to have some way of getting the same key. And I'm going to have some way of getting that shared key to you. Well, the issue with this is, well, in order to securely share a key, well, we're going to need a secure method of communication. But the whole point of sharing this key is so that we do have a secure method of communication. So we have a chicken and the egg problem where in order to securely communicate, we need to share a key, but in order to share a key, we need to be able to securely communicate. So symmetric encryption runs into that issue. Back in the day, the way they got around it was they hired a bunch of people to literally run the key, to take a padlocked briefcase, go up to you, and give you the key. Obviously, it's not really good, especially in the internet. So we get something called asymmetric encryption. Asymmetric encryption has what we call a key pair. So every single key will have a public key and its corresponding private key or secret key. The public key has a very special property in the fact that the public key can only encrypt data. You cannot use the public key to decrypt the data. And you can only decrypt the data by taking the secret key and decrypting. So now this gets rid of the whole key exchange problem because I can just generate a key pair. I keep the secret key, and I could just put the public key all over the internet, and I don't really care. So if somebody wants to send a secret message to me, what they're going to do is they're going to find my public key, encrypt the piece of plaintext with it, and now at this point, even if somebody has my public key, they can't decrypt it. I receive the ciphertext, and I take the secret key, and I decrypt it back into the plaintext. So asymmetric encryption allows for sort of communication over the internet without the need for that key distribution problem. Bad thing about asymmetric encryption is that it is dreadfully slow. And this is because the operation it uses, for example, RSA, it involves taking a very large number, our plaintext, to the exponent of another very large number. I think 60,000 is the current standard these days. So it is going to be very slow, and I'm going to show you this because it is really cool. I like showing people this once I figure out how to exit. Yeah. Right. So I'm just going to get out of here. Right. Right, so I actually have a little script that allows me to benchmark a symmetric encryption scheme and asymmetric encryption scheme. So you guys should be able to see this. So I'm using a Golang RSA and AES, RSA 2048 and AES 256. If you guys are somehow watching, why not just set the key once and use the same key to encrypt all future data? Well, the question is, well, how do we set that first key? Because the issue with symmetric encryption is the fact that even to get that first key going on, I need a way to securely get that to you. And well, it's a bit of a chicken and egg problem again. So that's why symmetric encryption, that's the key distribution problem. For an Arduino, for example, can you just set it in the code? Yes, I can. The issue is that I typically assume that the server is the weakest point. So I want the server, if somebody manages to compromise the server, they only get public keys, which is literally useless. So that's why I like using asymmetric encryption for this project, as opposed to using a symmetric encryption scheme. But it's a good question, though. If you are considering, for example, a situation where you believe your server is secure, then a symmetric encryption scheme will make things very, very straightforward. But in my case, I don't trust my server in general, so that's why. Right, so let's talk about the speed demo. So what's going to happen is I'm going to generate 1 megabyte of random data. I'm going to try encrypting it with AES, and I'm going to try encrypting it with RSA. If you are watching this 6 years in the future, when it is the 2030s, well, 9 years in the future, RSA 2048 is no longer secure. You should have switched to RSA 4096, so please use RSA 4096. Don't use an insecure cipher. That is just my PSA. So let's see this in action. Go run speed demo. So for RSA, it takes around almost an entire second, 728 milliseconds. Yesterday when I ran it, was half a second. AES is 209 microseconds. So that is an order that is 1,000 times faster, and in fact, it is around 3,000 times faster than RSA. And I'm going to run it again because you can actually see something really cool. Take it. You can see that there's a noticeable delay with RSA, and you don't see that with AES. So that's just something cool that I like showing, just to show the sheer difference in terms of speed for symmetric and asymmetric schemes. And yes, key exhaustion, every use of the key reveals information about it. That might help. Yes, very good point, Ty. Yes, key exhaustion. That is something that I did forget. But yes, essentially the issue with a symmetric cipher is that the case for AES as well? I know that typically the convention for stuff like TLS is you compute a session key using an asymmetric scheme, but that is something that I will leave as an exercise for the reader to read up on the spec for TLS. Have fun with that. So that is symmetric encryption and asymmetric encryption in a nutshell. Next, there's one more thing I want to talk about asymmetric encryption, and it's the fact that with some asymmetric encryption schemes, I can switch the secret key and the public key around. So what that allows me to do is I can take a piece of plain text, encrypt it with my secret key, and anyone with my public key can decrypt that, the ciphertext back to its plain text. So from a secrecy perspective, it is a terrible idea because anyone in the world can read what I encrypt. But this allows for me to prove the authenticity of data as long as I keep the secret key secret. So let's take an example. Let's say I send you a message over the internet in plain text saying, "Hello, today is a wonderful day." But before that message arrives, somebody intercepts it and changes it to say, "Hi, you are a terrible person." Well, when you read it, you're going to come up to me all angry and be like, "Why'd you call me a terrible person?" And there's really no way for me to prove that I didn't send that message. So what I can do is, on top of sending the original plaintext message, I also send this ciphertext that has been encrypted with my secret key. So what you do then is you receive that plaintext and ciphertext combo, you set the plaintext aside, you decrypt the ciphertext with the public key, and you basically compare the two results. If it matches, then it means nobody has touched it. But for example, if the ciphertext decrypts to say, "Hello, today's a wonderful day," but the plaintext says you're a terrible person, odds are somebody messed with the message somewhere and you know it's not authentic. So that is the main reason. So that is a cool little property of asymmetric encryption, and that is going to play a huge role in our authentication system. So let's also talk a bit about hashing, because again, I mentioned asymmetric encryption is slow. So imagine if I'm sending something like a video, right? That's going to be 300 megabytes. So to encrypt that video using my secret key, it's going to take much longer, and that's going to be an issue. So what we want to do is we want to have some way of uniquely identifying that video without having to encrypt the original video itself. And that is what we call a hash function. From a high-level overview, a hash function looks very similar to encryption. You get a plain text, you run it through some function, and you get a bunch of garbage out the end. So the key difference is a hash function cannot reverse the garbage back to plain text. It's essentially a one-way function. With encryption, you have the ability, given that you have the decryption key, to reverse the process. So, but what a hash function does is because it creates a hash, that allows us to basically compress the data, a large file into a relatively small fingerprint. So we can think of hashing as just finding the fingerprint of a file. And it makes our life easy because, for example, something like SHA-256, that's only a 32-character long string, and that is exceptionally fast to properly encrypt. So that's hashing. And with these two concepts in mind, we get something called a digital signature. So I'm going to talk about digital signatures from two different perspectives. So first, we're going to start off with the perspective of the signer. So as a signer, I want to send some data over to the receiver. So what I do is I will take that piece of data and I run it through that hash function, and out comes a hash. Then I take the hash function and run it through the signature algorithm. The signature algorithm is just a fancy way of saying we're going to encrypt it with my private key. The reason why it's called the signature algorithm is also because some implementations like RSA do include padding as well as other stuff, as well as some transformation on the hash, but we're going to ignore that for the purposes of today's conversation. So we encrypt the hash using my private key, and we have a signature. And again, because we can't just send the signature, because even if they manage to decrypt the signature and get the hash, they can't push it back to the original data. So we send it along with the data over to our verifier. Verifier does, they take the data and they run it through the same hash function, and out comes the hash of the data. Then they take my signature and they look up my public key, they run it through the verification algorithm. Again, fancy way of saying they're going to decrypt my signature, and out comes the decrypted hash. They'll compare the decrypted hash with the hash generated from the data. And if they're equal, again, it means nobody has really tampered with it. If they do not equal, well, something has gone wrong, somebody might have tampered with the data. The nice thing about this is because the signature depends on my private key, you're gonna have a really hard time forging it, and you can't really change the data such that it hashes to the same value because a good hash function will make it virtually impossible. So that is gonna form the crux of sort of how our authentication system is gonna work. So this is gonna be our solution, right? So this is what we call a challenge response framework. So this is going to differ a little from sort of what we imagine with password-based authentication, where we just compute some transformation of the password and we send that. Challenge-based authentication framework is going to depend on some data being sent over to us by the server in the form of a challenge, and we compute a response, which is some transformation on the data, and we send it back to the server. So this is quite nice because the server allows you to essentially the server now can compute a unique challenge for every single client, and that decreases the probability of having a successful replay attack. In terms of key distribution, the client is going to have the private key, the server is going to have the public key. I did talk a little bit about why I wanted to use an asymmetric encryption scheme, mainly because if I have multiple clients and somebody managed to compromise the server, well, they're only going to get a bunch of public keys. The only way that they can forge an effective client is by compromising a single client, which means that they're going to have to get physical access to the client, which is good, which is a pain in the neck to do. So odds are they're not going to do it. So step one of this framework, the client is going to send a connection request to the server. Fancy way of saying the client is going to open a TCP tunnel to the server. Server is going to do is it's going to be able to determine the client's IP, and that is going to be our challenge. So it sends the client IP, after which the client is going to compute the signature of the IP as part of the response and send it back to the server. And the server is going to verify that signature. And if it's good, it will begin sending application data, or in this case, the client will begin sending data over to the server. So that is essentially a challenge response framework. Let's talk a little bit about the requirements. So yes, the human is out of the loop because this is happening automatically. There's no need for me to punch in any secret numbers or anything. It's compatible with or uses 8-bit processor compatible libraries. So yes, we are going to be using the Arduino crypto library, which has functions that are supported by all Arduinos. So that's nice. Standardized cryptographic implementation. So it's being implemented by someone else and it's being actively maintained. So that's good. Should provide a strong guarantee that it was sent by an authorized device. So we know that it is sent by the device if it checks out, because in order to create a valid signature, you're going to need the private key, which only lives on the authorized device. We know that the device is authorized because the server only has a limited set of public keys that it's going to check the signature with. And that set of public keys is going to be the set of allowed clients. And it should be reasonably difficult to forge. So I did speak at length about how it is exceptionally difficult and a pain in the neck to try forging a digital signature, because you're either going to have to get my signing key, or you're going to have to essentially do what we call a pre-image attack, which involves us essentially modifying a piece of data such that it hashes to the same value. And with a good hash function and under the uniform hash assumption, that probability of you doing that is 1 in 2 to the 256 for SHA 256. So if you're going to do that, I recommend buying some lottery tickets as well. So before I really talk about implementing it, I want to quickly pause, mainly because I would like some water, and also if you guys have any questions. So also check out the poll. Let me know if I'm going too fast or if I'm going too slow. All right. Right, so let's see. No questions? No questions? Great. Sweet. So let's talk a little bit about implementing it. So it's gonna be fairly straightforward, because we're mainly talking about the authentication portion. So we're gonna be using Arduino's crypto library for our embedded system. For the server, I'm gonna be using Salt, but that is gonna be something that's not really relevant to embedded systems, but I'll show you the code eventually. So let's take a look at the crypto library. So this is the library that we are using. It's implemented by Risk Weatherly. It's being actively maintained by Dr. Brendan Wiley. So if we take a look at the documentation, it has a bunch of algorithms on it. The ones we really care about are the public key algorithms. So there are 3 algorithms. Really, there are 2. Curve 25519 are the primitive operations on the Edwards 25519 curve. And we have P521, which is a standardized curve. We're going to be using the Edwards curve, mainly because if we take a look at our performance, if we go all the way down to ED25519, so the time it takes to generate a signature with the Edwards curve is around 5 seconds on an Arduino Uno, I believe. And with P521, 60 seconds, so around a minute. And I really don't want to wait a minute for my thing to authenticate with the server, so we're going to be using the Edwards curve. In terms of the actual functions, it is fairly straightforward. Essentially, the sign function, none of these really have a state. It essentially requires a signature buffer, private and public key buffer, message, and the message to sign and the length of that message. Right, so let's take a look at the framework I have. As an aside, all of this stuff is going to be on the GitHub. The link to the GitHub will be located in the hack pack. So check that out if you want some time if you want to just download that stuff and take a look at it yourself, try implementing it yourself. So this demo, we're going to be using 3 other libraries on top of our crypto library. This is just to facilitate communications between the client and the server. This is the Ethernet library. The EEPROM library is used to store our keys, but you can hard code it in your code if you're just testing things out. The SPI and Ethernet are for communications. Right, so a lot of this stuff, because I've implemented this thing on a Intel Galileo, because that thing has built an Ethernet port, I have some additional steps going on for initializing it. So I'm actually making a call to the Linux subsystem. That's going to depend really on your own Arduino's implementation, how you have your Arduino set up. If you're using something like an Ethernet or a Wi-Fi shield, you might not have to do this stuff. We also got 4 buffers, the challenge buffer, so our response buffer, and our 2 public and private key buffers. From reading from the EEPROM, I just have it stuffed in there sequentially, so I'm just reading directly from there. You can see that happening from load from EEPROM, starting from index to read 32 bytes. That's going to be our public key. And for our private key, it's going to be the next 32 bytes. So that's fairly straightforward. And again, this is going to be implementation dependent. So yeah, but what we care really about is how this handshake works. So what's going to happen is it's going to first connect to our server. Port is chosen arbitrarily. Server is a hard-coded IP address. It's going to wait until the server sends it the challenge. So it's going to read the data into the challenge buffer. It's going to ignore 0xFF, mainly because one, the challenge is encoded in UTF-8. 0xFF is not a valid UTF-8 character, and 0xFF is technically used by client.read when there is no data to be read. So it's just going to read and shove that into our challenge buffer. It's going to generate a signature, and if the signature has been generated correctly, if signature's length is greater than 0, it's going to send it back to the server. Theoretically speaking, at this point, if the signature is checked out, the server is going to continue. It's going to keep the tunnel open. Otherwise, the server is going to close the tunnel. And it's basically going to read some data from the server. I have the server sending ping, and it will respond with POM. So it is a fairly primitive setup, but it's a good way to show it in action. So what we're going to be implementing today is really the generate signature function. The generate signature function will take in the challenge and the challenge length by reference, and it is going to generate a signature from the given challenge. So let's do this. So to generate the signature, what we're really just going to use is we're just going to copy and paste this sign function over, and we're just going to pass in the parameters. So the buffer for the signature is the response buffer. Our private key buffer is called our priv key buffer. And public key is the public key buffer. And essentially the challenge and the challenge length are just passed in. So at this point, if I run this on an Arduino, it should, in theory, work perfectly fine. But there's going to be one major issue from a design perspective, and it's the fact that there's no way to know if this succeeds or not. Because if we take a look at the documentation, this guy actually returns a void, which means there's going to be no return code. And you can see that there is no parameter for it to pass, for example, an error code into. So that's going to be a bit of an issue. So what we're going to do on top of signing it is, because we already have our public and private key on the Arduino, we can also call this verify function to make sure that the signature has been generated correctly. So that's what we're going to do. So if this verify function does not check out, this guy returns true if it succeeds, false if it doesn't. So if it doesn't check out, then we're going to have some way of telling the rest of the code something's gone wrong, and it should kick out immediately. So we're going to need our signature. Signature is called our response buffer. Then we're going to need our public key. So the public key buffer, it's going to need the message and the message length to have something to verify it with. So we're going to need that. And last but not least, our challenge length. And again, if you remember taking a look at the rest of our logic, so if we take a look at here, so we know that something has gone wrong with the signature generation if the signature length is less than or equal to 0. And that's what we're going to do. So if this fails to check out, we're just going to return -1. That typically is the convention for if something has gone horribly wrong. Otherwise, we will return the size of the signature, which is 64 bytes. So yeah, that works. Now we're just going to check this guy to make sure. Yep, so it compiles. Right, now let's talk a bit about the server code. So let's sample server. So the sample server essentially is implemented in Python. We are using the salt library for its cryptographic functions. And what it's going to do is it's going to listen on this IP address and port. And once something connects to it, we get the connection as well as the socket, as well as the address. And what we're going to do is we're going to send the address over to the Arduino as our challenge. UTF-8 encoding, we first send the length of it, and we wait for 64 bytes as part of the response. And then we're going to call verify challenge. Verify challenge, what we're going to do is we're going to load our public key, which will be on the server, generate and use it to verify the challenge as well, using the IP address and the signature given by our Arduino. And once that checks out, if it checks out, it'll return its IP address. If it fails, it'll return none. So if it does check out, we're going to send ping, and we will wait for POM. Otherwise, we will close the connection. So it's fairly straightforward. So let's see if this thing works. So Python 3, sample server. Right, so we have our server running. And oh no, I already loaded it when I tested it. So pretend you didn't see that. Right, so I just load that stuff on our Arduino. We're going to pull out our serial port. So serial monitor. So serial monitor here. The serial monitor. And right, there we go. I should be able to see this. So you can see it is reading ping from the server, which means the server is successfully sending stuff over to the Arduino, which means life is good. Now, we can also show that this is actually doing what it's supposed to do by using a tool called Wireshark. Wireshark is a packet capture utility, which lets me basically listen to all of the communications that is happening from my laptop. So this is Wireshark. I'm going to show you the raw packet captures. So the device we're looking on is my Ethernet port, so EN01. Right, so let's see. We should be seeing a bunch of stuff going on here. And yes, we do. Cool. So let's take a look at some of the packets. So my server is .29. The device is the Arduino is 177. So we can take a look at what's going on here. So the packets we care about have the push flag to it, which implies that there is actually data. Acknowledge flags and synchronization flags are TCP overhead packets, which are used mainly for the protocol itself and not really affected by any application data. So let's take a look. So first thing we see is the server is sending 1 byte to the Arduino, and that is the length of the challenge. So 0D, that's hexadecimal for 11. So then our Arduino is going to acknowledge it, and it will send the actual challenge, which is the IP address. And we can actually see it here in the hex dump. This is the data that is being sent. Arduino is going to receive that data and it's going to compute the signature. So we see that from this metadata, we have a 64-byte blob of data that is going to be our signature. And you can see that being sent over to the server. And because it checks out, the server responds by sending the length of the data. So where is it? 4, telling it there's 4 bytes coming your way, and ping. And you can see our Arduino responding with pong before closing the connection. So that just goes on to show how it works. I can also show you that from a trivial attempt at connecting to it, that it's not going to work. So I'm going to close without saving. So I can try to open up a connection to my server. So 192.168.129.7. So you can see it sends me my IP address as part of the challenge. I'm going to try just responding with garbage. Hey, this is my signature. This is 64 bytes in length. But you see, it just closed it. It does not like me at all. So that just shows that the authentication system works against these attempts. And also, you can also see from the Wireshark packet dump that the 64-byte blob of data, you don't really get much information out of it. And trying to even replay it probably would not work because the IP addresses are different. So, right, so that essentially brings me to the end of what I really want to show you guys. So I'm gonna, before I open the floor up to any questions, I also wanted to talk about some other applications of this because I realized that the example I gave was a fairly contrived example in the way where this is an Arduino that periodically communicates with the server. But if we flip the roles around where the Arduino is the one verifying the request, you can see something like, for example, a smart lock. If you send a smart lock or request for your phone to unlock, you want some form of authentication. You don't want anyone just to figure out the magic packet to send to the Arduino and have that thing unlock. So that is another example of some applications. If you flip the roles, you'll see a lot more need for authentication, especially if the Arduino is controlling something physical. So that's just some thoughts that I wanted to leave with you guys. So there's around 15 minutes. You guys seem pretty good with the content as well as the questions. So I'm just going to open up the floor to any questions. If there aren't any questions, I'll chill out until around 5 p.m. Then I'll be monitoring the Discord for any last minute questions. So yeah, thank you all very much for showing up. Thank you. Yeah, hopefully it made sense. Hopefully you guys managed to learn something about it. Hopefully I didn't confuse any of you guys. It's pop quiz. If we go back to the start of the whole thing, hopefully you guys are also able to understand how it is. Oh, hey, I see someone from the CSE. Hello. Yeah. Yeah, I'll chill out for a bit. Hi. Great seeing you again. Yeah. Are there any additional questions? Yes, no. This one. Am I going too fast? Did anyone respond to the poll? They did not respond to the poll. That makes me sad. Okay. Yeah. All right. If there are no remaining questions, I will hop off. I will be available on Discord. Well, I'm not actually going to hop off. I'm just going to turn off my video and my microphone. I'm going to continue monitoring the chat until 5 o'clock. Then I'll be off and I'll be monitoring Discord for any last minute questions. But again, thank you all very much for coming. Do hope you guys learned something. And yeah, have a great rest of Hack the North, I suppose.